You are welcome to MTH 202 class. In this lecture, we shall consider rank of a matrix. As we recall, a matrix, say A, of dimension, say n by n, can be written as follows. We can write it as A with entries, say A11 to mean the entry in the first row, first column. We have A12 entry in the first row, second column, and you can continue up to the last entry in that first row, which is entry in the first row, the nth column. I'll move to the second row. We have A21, A22, and we continue to the last entry in the second row, nth column. This can be continued up to the mth row, that is M. We have M1, we have AM2, and this procedure can be continued to the last entry at the mth row, nth column. Okay, so generally, a matrix or a matrix of dimension m by n can be written as of course, here m is the number of rows and n is the number of columns. And what do you notice? If you observe that m is equal to n, then we refer to A as what? A is a square matrix. A is a square matrix. Further, in your elementary maths or in elementary mathematics MTH 101, you must have been taught that a matrix having just a single row or a single column is referred to as vectors. So, precisely, if a matrix has just one row matrix, for instance, such is referred to as such is referred to as row vector. But if it has just one column, such is referred to as column vector. For instance, if I write this A1, A2, and goes on and on to having n columns. Because this has one row, this is referred to as row vector. And you can guess what the column vector would be like. An example is this B1, B2. You can continue up to the nth row. And Of course, this is referred to as, simply put, column vector. Now, what is the bearing of this concept to determining determining the rank of a vector? So we move on to definition. Definition. What is the rank of a matrix? Rank of a matrix. Well, keep in mind that the concept of rank of a matrix is a very important basic concept for understanding properties of matrices and also linear systems of equation, which you may have encountered before now. What then is the rank of the matrix? Okay, all right. The rank of a matrix, say A, is, simply put, the maximum number of linearly independent row vectors That is just a simple definition. Of course, take for instance, let's go back to the n by n matrix we wrote earlier. You observe that the entries here, there are entries in the first row. Entries here are entries in the second row. And you go on and on to entries in the nth row. Now, the definition for the rank of this matrix now, say A, you are then to look at linearly independent row vectors. That is linearly independent rows. So the number of linearly independent rows in this case will give the rank of the matrix. Okay, an example should convince you. Let's consider an example. Example. Suppose you are to determine the rank of this matrix. Let's call it A, which is written as on the first row you have 1, 2, 3. On the second row, you have 3, 2, 1. And the third row you have 2, 4, 6. So how would you determine the rank of this matrix? The question we should ask ourselves is, what are the row vectors? So if you look at the matrix here, solution, you observe that the first row, let me represent it by this vector. I'd like to use this symbol, permit me to use that, U, and then I write the vector as 1, 2, 3 to indicate the row vector for this matrix A, that is the first row. Then the second row, I will use the symbol V. I want to write 3, 2, 1. That is the second row. And you can guess what the third row will be. Let's use W, which will become 2, 4, 6. Now, by definition, the rank of A is simply the number of linearly independent vectors. So we need then to check, are the vector U, V, W linearly independent? If they are linearly independent, then we have 3 vectors that are linearly independent. And that would mean the rank is, simply put, 3. However, if U, V, W are not linearly independent, then the rank of the matrix we have to reduce, since the number of linearly independent vectors might not be up to the 3 number of vectors that we have. So let's see, how do we check whether they are indeed linearly independent vectors? You recall from previous lecture, as taught by Dr. Adiro, you recall that to check if U, V, W are linearly independent, you consider the linear combination. Say you are given alpha, beta, gamma. Well, you don't know their value. They are scalars. And of course, you wish to, if you can, determine their values. They are scalars. You check the linear combination alpha U plus beta V plus gamma W, which of course we want to have to be 0. If all of alpha, beta, gamma each is 0, then of course we are sure that U, V, W are linearly independent. But if at least one of alpha, beta, gamma cannot be 0, then we are sure that the vectors are linearly dependent. Okay, so let's see. Well, from here, we see that before we make any further deduction, observe U and W. Notice that W here as a vector, which is 2, 4, 6, can simply be written as 2 in bracket 1, 2, 3. Okay, and of course, this simply will give 2 multiplying U. That is W and U, they are related. W and U, they are related. And as a result, the point is that W and U cannot be linearly independent of each other because W relates U. Of course, the operation being carried out here has already assumed that the vectors chosen, they are from a vector space, and that is why we refer to them as vectors anyway. So the conventional operations of addition and multiplication by scalar odd. All right. Now, it is clear that, of course, indeed, U and W are dependent on each other. And as a result, the first equation that we wrote here is such that alpha and beta and gamma, that is, they might likely not be equal to 0, or better still, alpha, beta, gamma will not all be, that is, each be 0. Yes, so as a result, U, V, W are not linearly independent. And this is highlighted from the fact that W and U are related. So the rank cannot be equal to 3, since we do not have linearly independent rows to the U, V, W. So what next do we do? Well, since U and W are related, you can check the case of U and W, U and V, or W and V. Let's check that of U and V and see if they are linearly independent. And then, if the two are linearly independent, that means the number of linearly independent rows now, that is the maximum now, which you are looking for, the maximum number of linearly independent rows will become 2. So let's see. We move on. So we check, consider the case in which we have alpha U plus beta V, which is now equal to 0. So this will imply alpha U from the above question. Let's see. U has value 1, 2, that is entries 1, 2, 3. And V has entry 3, 2, 1. So let's have them here. Alpha U, we have 1, 2, 3, plus beta V. V is 3, 2, 1, and of course, this will give us 0. And of course, in component form, how do we write this? Well, before writing it in component form, we can have this to be written as alpha, 2 alpha, 3 alpha, plus 3 beta, 2 beta, beta, and of course, equal to the right-hand side. The 0 is simply 0, 0, 0. Okay. Now, further simplification, following the usual addition on our vector space, we have alpha plus 3 beta is equal to 0. And what do you think we have again? 2 alpha plus, what do you think? 2 beta will give 0. And we have the last one, 3 alpha plus beta equals 0. But what are we doing? Wait a minute. What are we doing? What we are doing really is to see if it is possible that alpha, beta will not be 0. But if alpha is 0, beta is 0, then that will inform us that the vector U and V are linearly independent. That is what we are doing. All right. If you observe from the first equation, you observe that alpha is minus 3 beta, and if you substitute this in, say, one of the other two equations, for instance, if you substitute this in this equation, you observe that by some calculation, we obtain minus 6 beta plus 2 beta equals 0. And of course, if you simplify this, this obviously will give us beta to be equal to 0, 0, 0. And no doubt, it tells us that this beta, back to this first equation here, you observe that alpha will give us minus 3 beta, which is now 0, and that is 0. So alpha is 0, beta is 0. But wait a minute, we have a third equation to confirm. And of course, if you substitute beta and alpha, their value, substitute in here, you observe that we have 3, 0 plus 0, of course, will give us what we have at the right answer, showing that the equation that we have here is consistent. It has solution. Okay, wow. So this will then tell us indeed that the solution we have, which is unique, is alpha equals 0 and beta equals 0. What is the point? The point is that since we have this condition that alpha u plus beta v is equal to 0, then we are sure that u and v are linearly independent. Okay? They are linearly independent. Since they are linearly independent, what then do we conclude? The conclusion, therefore, is that the number of linearly independent vectors for this matrix, the maximum number of linearly independent vector is 2. Maximum number of linearly independent is 2. Thus, by definition, let's go back to the definition of the rank of the matrix. The definition says that is the maximum number of linearly independent row vectors of A that gives us the rank of a matrix. Hence, the rank of A, let me write it beside it here, the rank of A, which I will simply write rank A. Rank of A is 2. Rank of A is 2. That is it. So that is how we determine the rank of A using the concept of linearly independent vectors. All right. Exercise, assignments. Let me call it assignment 1. And you are expected to submit this assignment on the Google Classroom. Yes, via the Google Classroom platform. The assignment is use the above method, that is the method we just discussed now, to determine the rank of the matrix 5, 29, minus 7, 2, 6, 0, and 8, 16, and 4. So you can quickly pen that down In our next lecture, we shall consider another method, useful method, that we will apply in determining the rank of a matrix. Thank you very much for listening.